This video is going to cover random and systematic error. So just some definitions to start off with: accuracy and precision. They're best understood in the context of multiple trials. So accuracy is how close your measurements are to the true value, and this is related to both systematic and random error. And precision is how dispersed your measurements are. Basically, when you take a bunch of measurements, are they in like a tight little circle, or are they very spread out? And this is mostly related to random error. So as far as just the various combinations of precision and accuracy, this is a common example that textbooks use. For this target, basically we're looking at how tightly the x's are together. So these are like a dart hitting the target, and ideally the center is the true value. So this is a situation where the measurements are precise. They're they're tightly centered together, but they're not accurate. They're precise, but in the wrong area. They're a bit away from this true value. In this situation, there's accuracy, but it's not very precise. So it's accurate in the sense that like the average of these values is in the center, but they're not very precise. They're all very spread out. This is a situation where it's not accurate or precise. The values are spread out, and also they aren't centering around the true value. And this is the best case scenario, where it's both precise and accurate. It's a tight little spread of the values, and it's centered right around the true value. So it's both precise and accurate. So random error is the first type of error I'm going to talk about, and it's mostly entangled with precision to the point that it's almost kind of like they're almost synonymous. Like when there is high precision, there's low random error, and when there's high random error, there's low precision. So random error is something that's kind of expected with instruments, because instruments are imperfect and people are imperfect when they're reading instruments and when they're collecting data. An example is like a scale that's off by like plus or minus 0.005. The key thing that makes it random error is it's plus or minus. It's kind of going back to before, where like these values, there is like kind of random error, but balanced out with many trials, it does kind of average around the true value. So this is like on the y-axis here we have the true value. That's what's plotted with this line, and the observed value are these dots. So there's random error, kind of plus and minus values from the true value, but overall, like, it's on average very close to the true value, because sometimes it's below, sometimes it's above. Another way to look at it is like if, let's just say, we repeat a study over and over and over again, and to the point that like these relative risk values we get between the exposure and the outcome, we have a distribution of them because we have like 10,000 times we repeated this study. Let's just say that the true value is a relative risk value of 1.5, and that's the value we get most of the time. But due to random error, there's times when we get a relative risk value a little higher, a little lower. That could be due to just basically inaccuracies in the measurement, or just chance. So basically any values you're getting that deviate from the truth we can basically say they're due to random error. Systematic error is something that isn't due to chance, and we don't expect it to occur. It's not necessarily due to like the expected variability in an instrument. There's more like a systematic trend in what the error is, and it introduces bias. Basically, systematic error and bias are kind of synonymous. There's three major kinds: confounding, which I covered in another video, information bias, and selection bias. And this harms study validity, and that brings up just another set of definitions that I'll just touch on briefly, where validity is basically the freedom from these biases. So like, these are all things that threaten validity. If all three happen, the study would be completely invalid, but if some of them are happening, there might be harm to validity, but not necessarily completely invalid. But basically, the more valid a study is, the less it is influenced by these three sources of systematic error. Internal validity is when the results you get from a study are representative of what's really happening with your sample population. So if we have a group of like 1,000 people and there really is a true relationship between the exposure and outcome there, it's basically how much our results align with what's really happening in our sample population. External validity or generalizability is how much what we find in our study. So like assuming we did perfectly measure what's happening with our sample population, external validity is all about how representative our results are of the population as a whole, because that's usually the goal. We're not hoping to generalize our results to the sample. The sample was used to generalize the results to some broader population. And external validity is how much the results in our sample are applicable to the general population, basically. So yeah, systematic error is entangled with accuracy, and basically systematic error isn't expected. Back to our thing here where it's like, where I said like with random error, it's like a scale that it's like plus or minus 0.005 grams. An example of like systematic error with a scale would be one that consistently overestimates values. So if this black line here is the true value and we consistently observe values that are higher, that's systematic error basically. And there's more insidious examples where it's not a consistent trend over the range of possible values. So as far as relating that image with the dartboard back to our back to random and systematic error, the situation where we have high precision but low accuracy is a situation where you would basically have low random error. There's not a lot of random error because there's not a lot of spread in values, but there is systematic error in the sense that it is deviating pretty heavily from the true value. And this situation, there's a low systematic error because it is centering around the true value, but there is decently high random error because there is variability in the results that appears to just kind of be at random. This situation, there's both deviation in the results, so like there's spread, so that's an indication that there's some random error, but they also aren't randomly distributed around this center value. It's kind of, they systematically differ from this center value all to kind of the top left direction. And this is a situation where both random error and systematic error are low because there isn't a lot of variability and there isn't systematic deviation from the center. So as far as accuracy, just revisiting that definition from before, it's like how close your values are to the true value. In reality, this is like a product of both random and systematic error. So like this distribution that I showed before of like if we repeated a study 10,000 times and the most of the time we'd get it near the true value. Let's just say in one of those times that we observed it being this different from the true value, it's kind of like still within the distribution of like it's not the true value, but the fact that it's part of this distribution kind of shows that it's not outside the realm of possibility that could have happened due to random chance. So that's how random error could influence accuracy basically. And systematic error is basically if like we're conducting the study with systematic error and we do that study that is plagued with systematic error like 10,000 times, the distribution itself will be centered around an incorrect value, so that will also be a threat to accuracy. Sample size is basically, I'd like to link the idea of sample size to error now. So basically on the y-axis here we have the error rate in a study, so like the amount of error it experiences, and this is sample size increasing from left to right. So as you increase sample size, you decrease the random error to the point that basically if you had an infinite sample size, in theory you'd have 0 random error left. Systematic error, on the other hand, doesn't change no matter how much you change the sample size. And that's one of the easiest ways to differentiate whether a type of error is random error or systematic error, is that if an increase in sample size can remedy that error, then it was random error basically. And this is from my sample size video where basically let's just say we have like a smoking group and a non-smoking group, And we have like lung cancer people, or sorry, no lung cancer people that are colored black and lung cancer people colored blue. Basically, this is like a pretty small sample size in the two groups. We have an odds of like 10 of the 40 people here had lung cancer, 5 of the 40 people in the non-smoking group had cancer. So we find that like if you're a smoker, you're 2 times more likely to get lung cancer. Just to show like the resiliency of this to sampling variability, because sampling variability is a classic example of random error. If you resample a population over and over again, there's gonna be some variability that's not necessarily systematic. So to simulate that, I'm just gonna swap these people, swapping like a case in the smoking group for a non-case in the non-smoking group. And basically that brought our odds ratio from 2 to 1.5. So just swapping 2 people had a pretty big influence on the measure of effect. And that's because the sample size was pretty low. Now the sample size is huge, and it's like 200 in each group. So we still have an odds ratio of 2, where 50 people out of 200 had lung cancer in the smoking group, and 25 of 200 had lung cancer in the non-smoking group. If we swapped again to simulate like a very small degree of sampling variability in the two groups, you can see that the odds ratio went from 2 to 1.9, so it only went down a little bit. And honestly, a sample size of 400 is still pretty small. So yeah, like that's basically, I guess it's small in some contexts, but yeah, so you can see that by increasing the sample size, it became more resistant to sampling variability, which is basically a way that I'm using to kind of show random error. Also, just showing how precision and error relates to significance is basically like the null value for an odds ratio is 1, and basically that would mean that you're just as likely to get the disease if you're exposed or not exposed. And how p-values come to be basically is like quite related to this idea of confidence intervals. And confidence intervals are basically the estimated value plus or minus some degree of error, and that depends on the confidence level you're choosing. 95% confidence is a common one, and basically as a function of the amount of error in the study, that it creates this band around the observed value. So 2 plus or minus like some value, and when this value encompasses the null, so basically we're 95% confidence that the true value, we found an estimated value of 2, and we're 95% confident that it's somewhere in this interval. And the fact that 1 is part of this interval that we're 95% confident the value is in, that's enough evidence to say that we're not, basically we have evidence that it might be 1 and there might be no effect. But this same value of 2, if we were to increase the sample size from 1,000 to 5,000, it decreased this confidence interval by quite a bit. It went from being this big to this big, and now we have a significant value. It's the same population, just with more people, and that's how basically sample size translates into significance, and basically showing how random error is related to sample size. That was not as clean as I wanted it to be, but yeah, just one more. If you bring it up to 10,000, it gets even smaller. So the bigger your sample size, the more precision you have, and basically that is similar to the concept of lower random error. So with systematic error, increasing the sample size doesn't help. The 3 main types, like I said, were selection bias, information bias, and confounding. And I'm going to do whole videos that focus on these 2. I already have one that focuses on confounding, but I'm just going to touch on these briefly, just because if I didn't, the video wouldn't really be complete, but I'm going to spend more time talking about it in another video. So with selection bias, it's basically when those who participate in your study are different than those who don't. And when these differences are related to both the exposure and disease, and especially if like the exposure-disease relationship differs in your group and the population at large, that's pretty severe selection bias. And it's basically like if interaction is something you have a handle on, it's almost like effect modification between being in the study and the study and the population at large. If you don't understand interaction, then that won't be helpful. But basically, yeah, the measure of effect, like the relationship between the exposure and disease, is different among those in the study than those in the population as a whole. So it can only happen when selection into the study is related to both the exposure and the outcome. Information bias, it's error in how the exposure and or disease is measured in participants. And when it's a categorical variable, so like basically like sex, male or female, when it's classified incorrectly, this is basically called misclassification. And when it's a continuous variable, like cholesterol concentration, it's called measurement error when that gets the wrong value. And it can be differential or non-differential. Differential is the more egregious of the two, and that's basically when the rate of misclassification is different depending on your disease status. And I imagine it's the same kind of thing if like the rate of misclassification of disease differs among exposure status. Basically, it's a differential because the rate of misclassification is different between two groups. In this example here, like in a case control, it's like if our exposure measure was different in accuracy between cases and controls. Non-differential is when is more, it's kind of like a little closer to random in the sense that it's happening to an equal extent in the disease positive and disease negative group. But basically, yeah, this is still information bias because someone's disease status is being misclassified, but at least it's not happening more in one group than another, where the effect that this is going to have on the measure of effect is difficult to predict, while the effect this is going to have is it's basically going to dilute the effect. So like if you are measuring like smoking and lung cancer and you expect it to be like 10 times more likely to get lung cancer if you smoke, but we're misclassifying people all over the place at random, we can anticipate that's going to dilute the effect. So we might find an odds ratio of like 2, you're only 2 times more likely to get lung cancer if you smoke, or we might get a non-significant result that's no evidence that smoking causes lung cancer. Which, like, in my opinion, that's a much less insidious type of bias where I guess that's like at a conceptual level. I think that like reporting a false trend is more problematic than missing a real trend. So yeah, non-differential, basically the worst it can do is hide a real trend and basically make your results not significant, which sucks, but at least you're not reporting something that's false. And the last one is confounding. And I have a whole video on this, but just really briefly, a confounding variable is something that's related to both the exposure and outcome, and basically distorts the relationship between the exposure and outcome when it isn't controlled. And for something to be a confounder, it needs to be causally related to the exposure, causally related to the outcome, and it can't lie on the path between the exposure and outcome.